Hey everyone, welcome. In this lesson, we will be building on what we have already done, as well as reviewing what we did at the end of last week with graphing rational functions, right? And so you learned a lot of information, and you're encouraged to take time to process and practice and think through it. You did not need to be an expert when you walked away from class last time. Just make sure you're thinking about what questions you might have. And as you watch this video today, write down your questions as they come up and have them somewhere so that you're able to easily ask them during class time or maybe in an email to kind of put that in the forefront of your teacher's mind. So what we're going to be doing in this video lesson is we're going to determine key features of rational functions, right? That's not new. You know what some key features are, right? Like some critical points, some where are the asymptotes. So that was something that was new. Any holes, the behavior, kind of, right? Like what happens around the asymptotes, what happens on the ends, that end behavior asymptote of a rational function from a given equation, and successfully graph, label, and identify some characteristics, right? Like domain, range, all that fun stuff. So we are going to go a little bit deeper into what happens with the range. We didn't really see any crazy situations with the range, I don't think, at least, the last time we saw you. And so we will look at some things. I don't know why I called it crazy, but some things that happen with the range of how do you actually figure out what the range is? Because it might not be all real numbers, but it might be, right? So how do we actually figure out what's removed? So that's what we'll be doing today. So let's start off with a few things from last time. So our goal of these three questions of f of x, g of x, and h of x, of these three functions, is to determine the asymptotes, both vertical and horizontal, and any holes of that may exist, right? So this might be a good place. I know it's early in the video, but to pause and try this, right? So what we want to do is we want to be able to have these in factored form so we can see if anything cancels, right? Because if something cancels, that's what creates a hole. And remember that a hole is a point. You can have more than one, but a hole is a point. So I need both the x and the y, right? Not just where does it happen, but at what height does it happen? So I can't factor the numerator, but I do know that the denominator of this one, of f of x, so I've got x plus 3 over x, so 4 and 2 is what's coming to mind. So positive 4 and negative 2. Nothing cancels, therefore I can automatically say that there are no holes. There's no removable discontinuities in this, right? But I do get vertical asymptotes then, right? You're going to have a vertical asymptote at x equals negative 4 and at x equals 2. These are the vertical lines that you would draw and label with this equation. The horizontal asymptote is determined by looking at the degree of the numerator and the degree of the denominator. And as we talked about in class, if it's bottom heavy, if the degree of the denominator is larger, it's going to grow quicker. And we can really focus on these two terms. And I mean, as you can imagine, if I plug in 1, I get 1. If I plug in 2, I get 2/4. If I plug in 3, I get 3/9. If I plug in 4, I get 4/16. The larger the number gets, the denominator is going to grow so much quicker because it's quadratic. I talked about, I think I only did this in one of my classes, but maybe you remember from Algebra 1, there was a question about the tortoise and the hare and who would win, and it talked about it, and it's well, maybe at first the quadratic isn't above it. I'm just sketching something. But by the end of it, the quadratic is going to grow so much quicker when you do that it's going to approach, in this case, 0 because the denominator is larger, right? You're never going to actually get there, but it's going to approach 0. So I'm going to get a horizontal asymptote at y equals 0. If we look at this next one, I'm going to start it off the same way. For g of x, I'm going to factor the numerator. What is that? X minus 2, x plus 1, divided by x minus 2. And oh my goodness, this cancels, right? And I get x plus 1. And this is wild, right? If I were to graph this, g of x, it's just going to look like a line, but it's going to have a hole at the point 2. And to find the y value, I'm going to plug it into here, the simplified version, 2 plus 1 equals 3. So it's going to have a hole at the point 2, 3. There's not going to be any vertical asymptotes right? This is literally going to look like a line with a slope of 1 and a y-intercept of 1 that has a hole, a removable discontinuity at the point 2, 3. This isn't going to have any horizontal asymptotes. It's top heavy. As you plug in larger x values, the numerator is going to grow quicker than the denominator, so it's going to shoot off to infinity. For h of x, my third one over here, I don't have anything to factor. Nothing cancels. I have no holes, but I do have a vertical asymptote at x equals 5. Okay. So the horizontal asymptote, right? These have the same degree. So as I plug in bigger and bigger x values, one's not going to grow faster than the other. They're going to grow at the same rate. So I'm going to look at their coefficients, and it's going to be the ratio of their leading coefficient. So it's going to approach the line y equals 1. Notice if I have a hole, if something cancels, I don't also have a vertical asymptote there. It's one or the other. They don't both happen. If something cancels, it's removable, right? I'm getting rid of it. Whereas nothing cancels here, so it's referred to as an infinite discontinuity because it's not going anywhere. Okay. So this was just to kind of summarize, this was the trick for horizontal asymptotes, right? So determine the degree of the polynomial in the numerator and the denominator, right? So you're looking at the degree of the numerator and the degree of the denominator. If it's top heavy, there's no horizontal asymptote. If it's bottom heavy, the horizontal asymptote is at y equals 0. And if it's the same degree, it's the ratio of their leading coefficients. So you would have y equals some number, which would be the ratio of a to b, right? And that needs to be in standard form. So if I had something in factored form, I would have to multiply it up. Let's look at some graphing problems, right? And again, I still have that. This is from last time. This is what we did in class. So here, let's find some key features and I'll graph it as I go. So the first thing I'm going to go ahead and do is, you know what? I might as well find the horizontal asymptote. If I look at the numerator and the denominator, they're in expanded form. So I've got here and here. They have the same degree. So my horizontal asymptote is going to be the ratio of their leading coefficients. So in this case, y equals 3. So I'll go ahead, 1, 2, 3. Y equals 3, labeled as you go, is my horizontal asymptote. Okay, now let's factor it. I can factor out a 3x in the numerator, and then I would be left with an x minus 4. And this denominator is going to factor into x minus 3, x plus 1. Nothing cancels, but I now know that I have two vertical asymptotes, one at x equals 3 and one at x equals negative 1. So 1, 2, 3. X equals 3, and 1, 2, 3, x equals negative 1. So there's no holes, nothing canceled. So now let's take a look at, let's find the x-intercepts, right? The x-intercepts are going to happen where your y value, where the function equals 0. We don't care about the denominator because if you have a fraction that's equal to 0, I could have 0 over 87, right? That's 0. I could have 0 over 42. I could have 0 over negative 624. These are all 0. So I'm really looking at where is the numerator equal to 0. So I'm going to actually erase that because that's going to get in my way. I'm going to take my numerator, 3x times x minus 4 equals 0, and I can use the zero product property, right? 3x equals 0, I get x equals 0. X minus 4 equals 0, I get x equals 4. So I have two x-intercepts. They're points, right? 4, 0, and 0, 0. So let's graph those. 0, 0, 1, 2, 3, 4, 0. Okay. Am I missing anything else? I need the y-intercept. I think I already know it. right? The y-intercept's going to happen when I plug in 0 for x. I like to do that in standard form sometimes, because what happens here is no matter what, if I plug in 0, that numerator is 0, my y-intercept is 0, 0. If your x-intercept is y0, so is your y-intercept. It has to be. And you can't have more than one of those. So before I even worry about the domain and range, let's go ahead and let's actually figure out what this looks like. So we know that at the ends, it's going to be approaching 3, right? That's your end behavior asymptote. So I want to figure out what's happening at some of these other places. I might be able to just predict it, right? It's got to approach these. So I know here it's got to go up, right? It's got to go down. Like it has to. It can't like come back down and around. Like it can't do that because you can't create other x-intercepts, right? So something similar over here. I know that this doesn't exist down here. It literally can't because I can't create an x-intercept that's not actually true, right? That's not valid. I only have these two x-intercepts. I can't create more. Same thing over here. Like I can't create more than it actually has. So let's say I plugged in a really, really, really negative value. I'm going to get, if I plugged in like negative 10,000 or negative 1,000, let's just pretend I'm not actually going to get it. But if I did that, let's look at factored form. 3 times some negative number is going to be a negative. A negative minus a negative is going to give me a negative. Divided by, that'll be a negative. That'll be a negative. Oh, I'm going to get a positive, right? I know this whole thing has to exist up here. Like it has to. I can't make, it's not going to go down because it can't. Then let's see like what happens if I went like to the right or to the left. Again, like I can't have something that like loops around and comes back down because I can't create another x-intercept. So my assumption is going to be that it's something like this, right? But I can plug in values and see, like if I were to plug in 1, I'm going to get, I do it in factored form, that'll be positive, that'll be negative, that'll be negative, that'll be positive. I'm going to get a negative over a negative. What happens if I plug in 1? 3. What was I doing? I literally lost my train of thought. I'm plugging in 1. I lied. My prediction was wrong, right? It's not down here. Watch what's going to happen. This is pretty cool. So if I plug in 1, I actually got a positive number, right? So, oh my goodness, it's going to go through the asymptote. If I plugged in negative 1/2, right? Nothing crazy, just like negative 1/2, I'm going to get, that'll be negative, that'll be negative, that'll be negative, and that'll be positive, right? Negative 1/2 plus 1. So I'm going to end up with a positive or a negative, which is a negative. So I know it's going to go down on that side, right? So again, your horizontal asymptote is referred to as your end behavior asymptote because at the ends, that's what it's approaching. You are welcome to like plug in some more values if you're like, I want to figure out what some of these points are. You can cross, very strange, but you can cross a horizontal asymptote. You can. So looking at this visually now, your domain is going to be all real numbers, but x is not going to equal to 3 and negative 1, right? Or maybe you're writing it as an interval and you've got negative infinity to negative 1. Union, negative 1 to 3. Union, 3 to infinity, right? It's good to know that there's different ways to represent it. What about the range? Your range is actually all real numbers, right? You might have thought, hey, I can eliminate 3 from it, but it actually is going to cross it. And here's how we can check that. And we're going to talk about it a little bit more in this lesson, but I can actually say, well, is that an okay range value? Let's take that questionable range value, 3, and let's set my equation. I'll just do it in standard form. 3x squared minus 12x over x squared minus 2x minus 3. Let's solve this. Right, I'm going to multiply both sides by the denominator. 3x squared minus 2x minus 3 equals 3x squared minus 12x. I'll distribute that 3. 3x squared minus 6x minus 9 equals 3x squared minus 12x. And let's solve this. Those 3x squares are going to cancel. I'm going to add the 12x so that I have a positive and add the 9. Right? And when I divide by 6, I get x equals 9 divided by 6. What's that? 3 halves. That's 1.5. Whoa. I actually have a point, right? That's an okay x value. That wasn't one of the ones that was kicked out. How wild is that? So I can actually figure out that this point right here where it crosses it is the point 3 halves 3. And that's why it's not removed. And so we're going to talk more about things like that with the range. Like, what if I didn't have the visual? Like, how do I do this? And we're going to talk about that in a few moments. Okay? This takes practice. Let yourself practice and try these out, and don't just do one and be like, got it. There's a lot of variety. There's a lot of things that can be thrown your way here, and give yourself time to practice. So let's do one more. So let's start it the same way. I'm going to start with the horizontal asymptote. And the horizontal asymptote, oh, notice this is negative actually. It is bottom heavy, so I'm going to have a horizontal asymptote at y equals 0. Graph and label. I'll then go ahead, I'm going to put that negative in the numerator, negative 4. I'll factor out an x, and you've got x minus 3 left over. So I don't have any holes, but I have 2 vertical asymptotes at x equals 0 and x equals 3. Graph them clearly. X equals 0, 1, 2, 3, and x equals 3. Okay, x-intercepts and y-intercepts. So your x-intercept will happen where the function equals 0. This is never going to equal to 0. So there's no x-intercepts. We're not going to be crossing this. So that means that that is actually, like, I could check it, right? I could check that, and I'm going to see 0 equals negative 4 over x times x minus 3. And then when I multiply both sides by the denominator, I'm going to get 0 equals negative 4. That's certainly not true, right? That's a false statement. Therefore, if I go ahead and I did the range, this would be all real numbers, but y does not equal 0, right? Kind of like I did the other one. I checked it. I was curious about it. It never equals it. So for the y-intercept, I'm going to plug in 0. Oh, no. There's no y-intercept either. When I plug in 0, I get 4 over 0, which is impossible. Okay? So I actually have no points that I can actually check. So I might want to plug in a point and get something so I can kind of see where I'm going here. So let's say I plugged in 1. Right? Negative 4 over 1 times 1 minus 3 is negative 2. So I get positive 2. 1, 2. Right? Give yourself something reasonable to check. If I plugged in 2, I know that it's not going to cross this, so I know that I'm going to have to be like going up this way, but I can get myself a little more. If I plug in 2, I get negative 4 over 2 times 2 minus 3 is negative 1. I get 2 again. Oh, goodness. What is going on there? Whoa. How do I get out of this? Oh, that was interesting. That point is 2, 2. Right? And I can kind of figure out that it must do something like this. Oh, goodness. I'm not going to touch the asymptote. It's going to approach it. Not going to go down because I don't have any x-intercepts. So then, I don't know, maybe I want to see like what would happen if I plugged in 4? Is this going to happen? I really just want to know, like, is it going to happen above or is it going to happen below? My guess is that it's below, but we can kind of, let's see. So if it's, let's plug in 4. That's going to give me negative 4 over 4 times 1. Negative 1. Yeah. that's probably all I need. Like I can get that, but I know now it's got to approach this on the end. It's not going to go up because there's no other x-intercepts. So my last thing that I need to check is what's happening over here. And so I can plug in whatever I want. Let's say I plugged in -1. And again, you don't need to get these points but they might be helpful. So that would give me -4 over -1 times -4. So -4 over 4, which is -1. Right? So that's down here. Whoa, that should look a little more curvy, but that's okay. Right? So the domain would be all real numbers, but x is not going to equal, I could have done this earlier, 0 or 3. They don't all look the same. You need to practice. You got to practice. You guys got this. So now let's look a little bit more about the range, right? And so you can do it visually as we saw, right? But we want to check, like, I could have something, this might be a hole, but it's a function, like it could have the horizontal line test, right? Like this could exist somewhere over here. Like clearly this y value, this height is fine somewhere else. So I don't need to remove it. Like it would be removed as an x value, but it wouldn't necessarily be removed as a y value. And as you're seeing, like we can pass through horizontal asymptotes because there are end behavior asymptote. And so we want to look at a little bit more, how do we find that algebraically and not just rely on it graphically, because together they can really give us a lot of resources to use. So here's what we're doing, and I kind of just said this. So we want to look at suspects, right? So that is the y value of your horizontal asymptote, could be more than one, and the y value of any holes. So you might be checking quite a few values. And so then what I did on that first problem is I replaced f of x. So this is plug in with each suspect and solve the rational equation. Did you get a good x? Well, what's defined as a good x? Something not removed from the domain. Right? Like if you already know, like that's a bad x, like I had to kick it out. That was something that like it was divided by 0 at some point in the original equation. If you get a good x, like we did on that first example, right, on this one back here, I got a good x. This is referred to as a good x. It wasn't something I kicked out, right? It wasn't something I had a hole or a vertical asymptote at. Therefore, it was not, that y value of 3 was not removed from my domain. That's what I'm getting at here. If you get a bad x or no x, right here, I got no x. X went away. That would be a case to kick that y value out of your range. Right? So we're doing this a little bit more algebraically. So if we take a look at these three, and I'm going to start it with you, and then you might want to pause the video and give it a shot. Right? So these are the three that we started with on the warm-up. So you've got x plus 3 over x minus plus 4, x minus 2. So for the domain, we know that it's all real numbers, but x is not going to equal to -4 and 2. I didn't have any holes. And then I also knew that I had a vertical asymptote at x equals -4 and x equals 2. Sorry, I wanted the horizontal asymptote. It was bottom heavy at y equals 0. We can't just jump to the conclusion that 0 is removed from the range. What we're going to go ahead and do is say 0 equals x plus 3 over x squared plus 2x minus 8. And we're going to solve this for x. So I'm going to multiply both sides by x squared plus 2x minus 8. Well, anything times 0 is just 0, equals x plus 3. Subtract 3, and I get -3 equals x. Is that a good x or a bad x? Well, it wasn't. I didn't kick it out. That is referred to as a good x Therefore, the range, I'm actually not kicking anything out of it. The range would be all real numbers. If I were to graph this, and when I graph this, my range is all real numbers. I would be going through the horizontal asymptote. It exists somewhere. There is a range value of 0. Like, you will get an output of 0 that is okay. And it would happen when I plug in -3, right? I might have seen that when I tried to go figure out, like, oh, what are my x-intercepts? Take the numerator and set it equal to 0. Okay? So this is how you're doing it algebraically, which is an important thing to show and know how to work through. And it helps you with your graphing, with your visualization of it. In this case, in this second one, we factored the numerator, x minus 2, x plus 1, over x minus 2. Those canceled, right? And when I plugged it back in, I got a whole at 2, 3. So the point that I want to check is 3, right? The y value of the whole. I didn't have any horizontal asymptotes here, right? It's top heavy. So I'm going to take my equation and say 3 equals x squared minus x minus 2 all over x minus 2. And let's remember the domain here. What are you kicking out of it? It's all real numbers, but x does not equal 2. That's the only thing it can't equal. So when I go to solve this, I'll cross multiply again. I'll multiply by the denominator again. And that's going to give me 3x minus 6. I distributed the 3 equals x squared minus x minus 2. I still have an x squared, so I'm going to get it all on one side and equal to 0 so I can factor. X squared minus 4x plus 6, so plus 4. I think that's a perfect square. X minus 2 squared, isn't it? So x minus 2 has to equal to 0, so x equals 2. Oh, well, that's something we kicked out. That's a bad x, right? It's not an x that is allowed to equal. Therefore, the range would be all real numbers, but y does not equal to 3, right? That means that I'm going to remove, it doesn't exist there. It's not like it exists somewhere else. And then finally, this last one we had on the warm-up, let's think about the domain first. So it was all real numbers, but x does not equal to 5. This has no holes, but this does have a horizontal asymptote at y equals 1 because they're the same degree and it's the ratio of the leading coefficient. So I'm going to go ahead and say, I'm going to check this. 1 equals x plus 3 over x minus 5, cross multiply, or multiply by the denominator, x minus 5, right, equals x plus 3. When I go to solve this, those x's cancel out and I get 0 minus 5 equals 3. Negative 5 equals 3. That doesn't make sense. I lost my x, right? So this was a bad x. This is the case of no x, right? And therefore, what I can conclude is that the range would be all real numbers, and I should kick that value out. I should kick that 1 out. Y does not equal to 1. I'm not going to be crossing over that asymptote. It doesn't exist somewhere on there. So let's put this into practice. And I really think this is a good opportunity for you to actually check your own understanding. If you haven't, especially if you haven't paused the video at all, stop the video now, check it, see how you're doing with this, and then come back and let's go over it. So hopefully you've had an opportunity to try this, and let's work through this. So the first thing that I'm going to go ahead and do is the horizontal asymptote. This is top heavy. I got no horizontal asymptote. Okay. So now I'm going to go ahead and I am going to factor out what I can. I can factor out an x, and I'm left with x squared minus 9, which factors more. I can factor out a 3, and I'm left with x squared minus 2x minus 3, which factors more. So this is going to be x times x minus 3, x plus 3, over 3 times x minus 3, x plus 1. Those x minus 3's will cancel, which automatically makes me know that I have a hole at the x coordinate of 3. So I'd be left with x times x plus 3 over 3 times x plus 1. For me to find the y value, I need to go ahead and plug in that 3 for x. 3 times 3 plus 3 over 3 times 3 plus 1. Right, so that's going to be, those 3's actually cancel. So that'll be 6 over 4, or 3 over 2. Okay, that's going to be my whole. Okay, so I do know that that gets kicked out of my domain, right? X isn't going to equal to 3. What else isn't it going to, it's not going to equal to -1 either, right? Because that's going to be a vertical asymptote. X equals -1. So I should probably start graphing some of this. I know at the ends it's going to either shoot off to infinity or negative infinity, right? Because there's no end behavior asymptote. X equals -1, and then I have a whole at 1, 2, 3, 1, 2, so like right here. 3 3/2. Okay. Let's think about x-intercepts. My x-intercepts are going to be where this equation, or I'm sorry, this function equals to 0. So I'm going to focus in on the numerator. So I'll do it right here in factored form. So it'd be at x equals 0 and -3. So at 0, 0 and -3, 0. Okay. Y-intercept, sure, I could totally plug it in, but what's going to happen if I plug it into the numerator? I get 0. And I already know that because I see this point. So now I kind of want to stop and I want to think about the range. What are the range values that I'm going to check? Well, my suspects are going to be a horizontal asymptote, which I don't have, and the y-coordinate of my hole. So I'm going to check 3/2 and see, does it exist at the level of 3/2 somewhere else? And if so, where? So I'm going to take my equation, and set it equal to 3/2. And now I'm going to solve it. I'm going to use that method of cross multiplying because I think that's a little quicker for me, but we'll see. So if I multiply 3 by all of this, it'll give you 9x, nope, 3 times 3 is, 9. 9x squared minus 18x minus 27 equals to 2x cubed minus 18x. Those 18x's are going to cancel, aren't they? And I am going to have, oh goodness. Oh, why did I do it with this one and not? Oh my goodness. I don't know why I didn't just do it with the simplified version. I'm over here trying to deal with a cubed, making my life harder. I forgot I simplified it, right? I might as well just do it with this. X times x plus 3. They behave exactly the same except for the whole. Right? So if I cross multiply, I get 9 times x plus 1 equals to 2x times x plus 3. 9x plus 9 equals 2x squared plus 6x. So, goodness, 0 equals 2x squared. I'm going to squeeze down here in the corner. Minus 3x minus 9. Does that factor? 2x and x. The only thing to do here is 3 and 3. Okay, so that's going to give me, I want it to be a -3, so it's going to be a -6 and a positive. 2x plus 3 equals 0. And x minus 3 equals 0. So x equals 3, and x equals -3/2. Whoa. That's right. If I plugged in -3/2, I'm also going to get this output of 3/2. If I plug, right, those are both good x's. I'm sorry, they're not both good x's. This is a good x. This is a bad x. But I got a good x, so I don't want to eliminate this whole because it's going to exist there somewhere else. It's actually going to exist at -3/2, right? I'm going to end up with a point that's like right here. That might help me graph it, actually. Right? Maybe I can see that, it's got to do something like this. Not approaching anything. Right? And same thing here. Oh, goodness. I don't like that. It's got to approach this. Then here it shoots off into infinity. Right? So that, I mean, when I'm talking about the range here, it's actually just all real numbers. Even though this y value doesn't exist over here, it does exist somewhere else. And that checking that allows me to actually find another point to help guide my equation. And I can think about if I plugged in a really, really negative value, I'm going to get a negative times a negative divided by a positive times a negative. Oh, it's negative, right? So where you can kind of check those different values. This stuff requires a lot of thinking and a lot of practice, and it's not like every single one looks the same. Like you really got to piecemeal it together and figure it out, but it is really neat when you're able to develop this composite. So give yourself time to practice and process and try this, and don't just do 2 and say, I've got this. Give yourself lots of time to practice. On your assignment, there's not much like graphing by hand. It's a lot more about identifying the features. So it's really up to you to just like make sure you're also practicing the graphing so you're not missing that skill, because sometimes that part can be a little bit difficult. So just give yourself time to practice that as well. And again, like hopefully you've written down any questions or points of confusion that you might want to bring up to us, or that you want us to address, and feel free to just email them along, or ask them as they come up in class when we see you next. So what we did today was we reviewed what we did in class last time, and then we really dove into like, well, what happens with the range, which is not something we talked about last time. Okay, it required a little bit more or something a little bit different, but hopefully that you understand what the expectation for checking the range is, and you know how to do that, and it helps you to graph it. So other than that, this is all I got for you guys. Make sure that you practice, make sure you complete your assignment, and gather those questions that we can help clarify anything you might need when we see you in class. Thanks, everyone. See you all soon.